Hey, Ollie,
Yes.
how you doing? Happy New Year.
Happy New Year. Wow, we have a nice nice attendance online here.
Cool. Are you the chairman? I've forgotten.
Yes, for today.
Okay. For today? I mean, there was a different chairman yesterday?
Today is George's day.
Yeah.
So I will be able to stay for about an hour, someplace between an hour and a half. So when I have to drop out, I'll just write you a note with my inputs.
Perfect. Yeah, that works. That works great. Okay, well, it's not MIT time yet, 11:05, but I think we can maybe start with introductions. Would that make sense? Okay, well, hello everyone. My name is Ollie DeVeck, and I will be chairing this doctoral thesis seminar. First, I'd like to introduce our candidate, and then talk a little bit about the procedure, and then George will start with his presentation. So first of all, you know, I know several of you in the room are on your doctoral journey yourselves, and there are different paths to a doctoral thesis defense. There's the direct path, which is like, you know, an arrow, like you go undergraduate, you usually finish at 22, then you do a master's, that puts you roughly at 24, and then you go straight for the PhD, and you'll be like 28 or 29 by the time you get to defend. Those are average numbers. And that's the direct path. And then there's the indirect path, which is that you don't do it that way, but you do other things. You have other experiences in your life, and you take the long road around. And I think today's candidate has chosen the long road, and that's George. And so let me tell you a little bit about George. So George is from Cyprus originally, and he went to the University of Oxford. And got a Bachelor of Arts in Philosophy, Politics, and Economics. That was 1988 to 1991. And you'll see, I think, in his dissertation, there, for example, there's some economic arguments that are made here, which, you know, I'm sure you learned some of that back at Oxford. And then he came to MIT. Actually, his first round at MIT was at Sloan. He got an MBA at Sloan. That was 1998 to 2000. He returned to his native Cyprus, and he's done many different things. He's been an entrepreneur. He ran several businesses in the energy efficiency space and logistics. And then he came back, and the first time I met George was in, I think it was in 2015. He came to see me and talked about Mars. And, you know, I love Mars. I think many of us believe that a human mission, not just a single mission, but humans actually establishing a footprint on Mars is very important for us as a civilization. So George made a very passionate case, but he had a very unusual path. But, you know, I quickly learned that George is very serious about this, and that he's made a big investment into that topic. And so he came back to MIT. But to ease sort of the path back to academia, I suggested that he maybe do a master's again, and that's when the SDM program came into play. And Brian, you're here. So George did the SDM program, graduated from SDM in 2018, and then very quickly became kind of indispensable as a head TA and really helped improve that program. And he's been working on the topic that he'll present on today really for the last 5+ years. He's won many awards. He's mentored. A lot of you that are in the room have benefited from George's leadership on several topics. And so without further ado, we're really excited to hear from George about his research. This procedure today is pretty straightforward. He's going to give a seminar first. That's 60 minutes or less. Maybe a little bit less. Please, only clarification questions, like short clarification questions. Then we'll have a larger Q&A, starting with the committee, the readers, and then we'll go into closed session, discuss the work, come up with a decision, and then inform everyone, including George, of course, the outcome. So with that, happy to see everyone. This is truly a hybrid defense. And George, it's all yours.
Thank you. So the title of my thesis project is Engineering Robust and Autocatalytic Architectures for Human Missions to Mars. And those who know me know that I always like to slip a Greek word in there. So autocatalytic is a word for something that can drive its own growth. Okay. Backup method. So the agenda today is that we will start with problem framing, which is that in this case, we will be studying missions across scales, which is something new and different. The approach is high resolution crew time modeling, something which hasn't really been done before, and it will help us to discriminate the performance of architectures across scales. The results that we will cover near the end are that larger missions are indeed affordable, valuable, and robust. And one of the conclusions is that crew time will be more scarce than mass in the future. So I'm kind of spoiling my own reveal, but there it is. So starting with problem framing, evaluating architectures over a range of scales. And we will start by looking at NASA's Mars exploration program. Now, the exploration of Mars has been going on for decades, and we've been exploring Mars with orbiters and landers and rovers, and most recently with one small plucky helicopter called Ingenuity, which has made, I think, 59 or 60 flights.
67.
67?
At last.
I'm behind. Okay, yeah. So, but these missions were all robotic. And really, the giant leap for the 21st century will be when a human first sets foot on Mars. So, sending humans is thought to be a way to turbocharge science and exploration. Humans are thought to be able to get results hundreds to thousands of times faster than robots because of their ability to discriminate and make decisions on the spot and to see things and use all their knowledge. So, and that's NASA's horizon goal, but the moon comes first. NASA aims to land the first woman on the moon this decade with its sights set on Mars for the next decade. And the moon is not just a destination in its own right, but it is also going to be the testing ground for Mars. NASA will test technologies and processes and strategies on the moon. Now, as part of its Moon to Mars strategy, NASA has recently published in April of last year a document called the NASA Moon to Mars Strategy and Objectives document. And there in that document, we see certain recurring tenets and goals, which are actually very interesting from the perspective of this research. And I think you will see later on why they're interesting. So recurring tenet 1, RT1, calls for international collaboration. RT3, return crews safely, mitigating impacts to their health. TH4, that crew health and performance is paramount and extended duration habitats are desirable. Recurring tenet 4, maximizing crew time for science and engineering. RT5, the long-term sustainability and increasing Earth independence of the mission. Now, many of these seem to point to larger missions. For example, progressively Earth-independent habitation really calls for larger missions. But really, I've reviewed the record of Mars architectures to produce this. And what we see here is that on the horizontal axis, it's a time axis. And then vertically, we have crew member days on the left axis times the, basically crew, it's the product of the number of crew on Mars times the endurance, times the time that they're on Mars. So it's a measure of how much human time is available, services of humans are available on Mars. And on the right-hand vertical axis, we have injected mass in low Earth orbit per crew member day on the surface of Mars. So since mass has been thought of as a proxy for cost, you can think of the right-hand axis as a cost per unit of benefit. So it's a cost per crew member day on Mars. The blue line is corresponding to the benefit. And what we see here is that there is a long-term trend over decades of this benefit proxy being in decline, and the corresponding cost proxy, specific cost proxy rising. So let's see why that is so. A review of the history shows that there has been an impulse to design for minimum viable size. What we see here in the boxes are many different NASA architectures designed from the 1960s up to recently. And again, on the horizontal axis, we have the injected mass in low Earth orbit, and on the vertical axis, the same benefit, the crew size times surface endurance. So cost versus benefit. We have to go back all the way to 1952 to the very first Mars architecture by Werner von Braun, where there was a plan for 70 crew. He quickly changed his mind, went down to 12 crew. And then by 2009, the DRA 5.0 provided for 6 crew. And the latest architecture is considering 2 to 4 crew. Now, the question arises, I mean, what about robustness when we minimize cost? I mean, we can see why there was an impulse to minimize cost. There was this perception that mass strongly drives cost, and crew size, we know that crew size drives mass. So minimizing crew size was a way to pursue minimizing cost. But what happens to robustness when we minimize cost? Well, so we will explore, to answer that question, we will explore a part of the design space that hasn't been looked at, which is larger missions with more mass, more crew, and more endurance. So the region marked with the X. So what happened to robustness? Well, the decades of scope cutting and mass trimming didn't actually buy safety for NASA. What we see here in this chart is the 31 different risks that are tracked by NASA's Human Research Program. And red is a classification of unacceptable that was assigned by the Human Research Program scientists. And this is a grading of NASA's own DRA 5.0 architecture. So one part of NASA had concluded that another part of NASA had designed an architecture that was not feasible and really not safe, with a 10% probability of loss of a crew member because of insufficient exploration medical care, among other unacceptable risks. One implication of small missions is that the crew has to wear many hats. So regardless of mission size, all the roles will be needed. We will need electricians and mechanics and geologists and biologists and physicians and computer specialists, whether we have 6 crew or 60 crew, we will need all these roles. So if you have a small mission with 4 crew, then they will end up wearing 6 or 7 hats each. So what you see here is data based on a report prepared by subject matter expert, Dr. Jack Stuster, I hope I pronounced the name correctly, for NASA. And this project was meant to identify the crew capabilities and abilities and also match them to roles to effectively carry out the mission. And the problem here is we see that the physician is also the computer specialist, and they have backup roles as a biologist and a mechanic and an electrician and the botanist. So, you know, we have to ask whether and how performance degrades when you assign so many roles to people in a high pressure, high risk environment, and to only 4 people who are on their own for 2 years or more. So that really prompts us to wonder what performance might be like with larger scale missions. Now, the nice thing is that larger scale is now an option. It wasn't before, but thanks to new developments in space transportation capabilities, we can expect potentially explosive growth in mass to orbit capacity with dramatically falling costs. And in terms of numbers, what that might mean, we might be looking at reductions in cost of 2 orders of magnitude and order of 100-day crew transits and order of 100 tons of payload to Mars with just single flight, which is unprecedented. I mean, Curiosity and Perseverance rovers are of the region of 1 or 2 tons. That's our capability right now, to land 1 or 2 tons on Mars. We're talking of 2 orders of magnitude. So besides falling costs and higher payload capacity and faster transit, what other benefits might we have from larger scale? Well, intriguingly, the International Space Station experience indicates that there may be economies of scale in the maintenance of environmental control and life support systems. What we see here is that when the ISS went from 2 crew members to 3, the time to maintain the life support systems on a per crew member per day basis went down from 1.5 hours to 1 hour. So there could be economies of scale from going bigger, and that makes it interesting to study larger architectures. Now, a review of the modeling work that has been done in this area shows that there are gaps in the modeling of impacts of crew size on mission feasibility and cost. One of the subject matter experts who has looked at all Mars architectures, Donald Rapp, concluded that there was relatively little discussion given to crew size, even though crew size is the most critical factor in determining the feasibility and cost of a human mission to Mars. Moreover, the crew time optimization models in the literature haven't been used to support trade studies between these variables of overall scale, robustness, and cost of a human exploration architecture. So we are missing something there, clearly. And finally, all the crew time models in the literature basically make a fixed productivity assumption, at least the ones I have found. And they certainly do not attempt to model the effects of what happens to crew productivity, what happens to economies of scale as the scale of a mission changes, because these might be significant effects, but they're not modeled. So this leads to the research question, to the gap in the research question. So the gap is that there is no systematic approach to quantify the relative benefits, robustness, and autocatalytic potential of Mars surface human architectures over a broad range of mission scales. The research question is that all other things being equal, either plausible and credible, large Mars surface human architectures, which can deliver more value, are more robust, and have a higher autocatalytic potential than the traditionally small Mars architectures. And then there is 3 hypotheses really wrapped in one, which are that within a given family of architectures, as defined by a scalable baseline architecture, which I will describe in a minute, a larger Mars architecture can plausibly deliver more value, be more robust, and have a higher potential for organic autocatalytic growth than a smaller Mars architecture. And so with this review of the literature and context, we're ready to pull everything together into a new framing for the Mars surface human architecture problem. So what we see here on the left is the traditional framing where crew size, surface endurance, and number of launches were handed down as constraints. And mission architects were trading technologies and transit architectures to try to come up with an architecture that closes, that meets these requirements, these constraints, and also is feasible, affordable, safe, relatively safe. And that's why mission robustness is a traditional intermediate variable in my view, because it was found, as we saw before, that DRA 5.0 wasn't really robust. And what I have done is that I have taken these variables and changed around what is a constraint and what is a design variable. So the transit architecture, from the perspective of the surface architecture, I made it a constraint so that it's a level playing field for all the surface architectures. They all use the best transit architecture, and we'll describe in a minute what that is. Mission robustness, I made that a constraint because just like somebody could say, let's design for low cost, somebody else could say, let's design for high robustness, and let's choose building blocks of architectures that lead to robustness. And I added scalability as well as a constraint, that the mission has to be designed to be scalable. So that's my choice of constraints, and someone else could choose another set. The new set of design variables, I've taken crew size and surface endurance, which were constraints, I've turned them into design variables. And I've added the number of nearby sites, 1, 2, or 3, as a design variable as well. The new set of intermediate variables now includes economies of scale and the effect of scale on productivity. So if you remember from the gap, those were not tracked in the models. We have to track them as intermediate variables so that we can calculate the effect on the outcomes and metrics. And to the traditional outcomes of life cycle cost and probability of loss of crew and mission, I have added new value metrics and robustness and autocatalysis metrics. And today I will talk about the value and robustness metrics, but in the interest of time, I will not mention the autocatalysis. Okay, so with that, the approach, the overall approach is to use a high resolution crew time model within an integrated architecture screening model, so a model within a model, to calculate plausible performance metrics for a scalable baseline architecture. So the first step is to define the scalable baseline architecture, and this requires coming up with feasible configurations at different scales, because a computer will not do that for you. You need an architect to say what is feasible. Then the decision variables are, in this case, the ones that will be varied to see the outcomes are 3: crew size, endurance, meaning the number of years on the surface of Mars, and the number of sites. And then to actually drive the crew time model, you need generators of events that require crew time. So these low fidelity submodels serve the purpose of generating activities that demand crew time, so that we can model the crew time that is needed. And then the next step, building on top of these foundations, is to come up with a costing model and an activity time model. So the latter is in 2 steps. We just define a list of activities, and then we have an equation that we use to calculate the time demanded per activity. Then to incorporate economies of scale, we will have to classify costs into which ones appear fixed, which ones are semi-fixed, which ones are variable. This will allow us to calculate economies of scale with respect to cost. And to calculate the effect of economies of scale on crew time, we would follow a similar example, a similar paradigm of abstracting activities into having a setup time and then a set of tasks which have a duration per task. Now, the last step is also to account for the effects of scale on productivity. And specifically, we'll be looking at how specialized is the crew, if you remember the hats, right? The task focus. So are there a lot of interruptions? Are they doing a lot of multitasking or not? And then are they learning? So as they repeat an activity, are they becoming better at it? And if we account for all these, I mean, no model is perfect, but at least this model will be an improvement over what we have been doing before. So that's kind of the goal, to calculate cost and time-based performance metrics, and then we can use them to compare alternative architectures and then choose among them potentially which ones to look into further. So let's start with the first step, which is defining a robust, scalable baseline architecture, which is this part of the equation. And the goal here is to, when we say scalable, we mean that the design variables, when we change them, we will see an impact of these design variables on the metrics. So there were 2 major parts to that. One was resolving the crew transit. So the fastest possible crew transit to minimize health risks for crew is 113 days on the outbound. And this is a result of work that I did with my colleague Keir. Actually, Keir led this part of the work. And the return would be 166 days inbound. So we chose conjunction class fast crew transits, departing from a high elliptical Earth orbit, refueling in full before departing, and then leveraging the Oberth effect to minimize the crew transit time. And the strategic goal of minimizing crew transit time was to minimize the effective dose of radiation they would accumulate and minimize the impacts to their health. And we give that same level playing field to all the architectures, small or large, so that we can see their performance when we give them the best possible transit architecture. Now, that means that some technologies have to be developed. So this would be a Starship class spacecraft as developed currently by SpaceX. Orbital refilling, the ability to produce propellant on Mars to refuel the spacecraft, and also some form of radiation shielding for this project, we chose polyethylene. Now, with this baseline space transportation resolved in the same way for all architectures, the next step is to design the scalable surface architecture. So we did that with the pale red dot concept, which was our response to the NASA Rascal competition back in June. We designed a two-village architecture, but the main idea for the scalable architecture is that it has to be multi-village. So two or more villages, they have to be far apart enough, but also close enough for self-rescue. Because we're talking larger architectures, we need robust logistics. So we designed a self-unloading star crane cargo ship with Dane Gleason. And with Francesco, we designed the modular habitat platform for easily scalable, supportable architectures. So what that means is that we can load two of these in a Starship, and then they inflate, and we have two-floor habitat modules. And we use the same habitat modules for everything. Now, each village will also use its construction capabilities to create permanent habitats. And the goal of creating permanent habitats is to reduce radiation to nearly zero, so that they can stay longer on Mars and do more science on Mars. And so the baseline architecture includes the capability to tunnel into competent rock and to construct large volume habitats in rock, so that the crew will be able to move into those habitats and shield themselves from radiation. So these areas include common spaces, farms, habitation, parking garages with docks for the rovers, and so forth. Now, all of this leads to capability-rich villages with a self-rescue capability. They are rich in energy, water, food, and time. That's the vision, that if you make them rich in all these resources, then they will be more likely to address any contingency. Think back to Apollo 13 and the plastic cover and the bungee cord and the sock and everything. Imagine the degrees of freedom when you deliberately design to be rich in everything.
And the duct tape.
And the duct tape, I missed the duct tape. So then the other big part of the vision is that they must thrive, not just survive. So that means taking into account what will the length of the work week be like, allow time in that work week for what we call expression-related professions. So this is a concept I developed with Dr. Alexandros Lordos. And the idea here is that crew should self-select an additional profession on top of their survival-related profession. So I might choose to be a chef or a Greek dancing coach, or somebody else might choose to be a journalist. So that enriches their own lives and the lives of the crew. And when we're talking 5 to 10 years on Mars, this could make the difference between success and failure. So then we need leisure facilities, private rooms. The vision includes social complexity and diversity to mitigate the isolation in a confined environment. So all of that was the robustly scalable baseline architecture. Let's come to the meat of the thesis now, right? The scaling and seeing the performance change. So this slide shows the configurations of the 17 architectures that I modeled and evaluated. And this ranges to up to 63 crew in up to 3 villages. I call the sites villages, and up to 10 years on Mars. And the naming system is 1225, stands for one site, 2 teams with 2 crew per team for 5 years. 1538G is one site, 15 crew, 8 years, but with growth capabilities. They have facilities to do this. 263 10G, so now it's 2 sites with 36 crew in total, 10 years in growth. 373 10G, 3 sites, 63 crew. And the two columns on the right, food and growth. So some architectures have 100% food, some have less. The reason for that is there was a step when the initial modeling showed that some architecture would simply not close at all if you try to overburden them with too many things to do. So there are other solutions to food where when you make only 4.5% of your food, the rest has to be freeze-dried and comes in from Earth. And likewise with growth, the smallest architectures do not have enough staff and enough crew on hand to maintain the tunneling machines, for example. So this is the explanation for these choices. So the next step here is that we model the effects of economies of scale on life cycle costs for all 17 Mars architectures. Let's see how this was done. So the key point here is that economies of scale in cost arise out of the structure of the equation. So the choice of the equation and the modeling approach allows us to see this effect come through in the numbers. And the life cycle cost for architecture A is the sum of systems costs, and systems costs are defined as the development cost, the sum of the development cost for each technology, plus the number of copies of that technology times the fabrication or production cost per copy. The next component is operations cost. So it's number of staff times program duration times fully loaded cost per staff member per year, like an average, which includes everything. And that 17 plus E design means that the program length is a fixed 17 years from, let's say we push the button now and we start designing our mission to Mars. The first person will land on Mars 17 years from now. So the program length is 17 plus the endurance of the mission, approximately. And then the next term is launch costs. So here what we have is the product of total launches times cost per launch. And the total launches include a constant of 63. So there is this big technology development program in these 17 years, which includes testing in low Earth orbit, in cislunar space, near the moon, on the moon, and then exploration, robotic exploration of Mars to identify the best site, because it's a big investment. I mean, you have to invest in finding the best site before you put all your chips there. So let's see an example at 3 mission scales, medium and small, medium, and large, and we'll see how that works. But sorry, before we do that, the last term I forgot to mention is margin. So the 40% includes the traditional 30% margin and 10% for outreach education. So this is like a provision that NASA typically adds on project costs. Now, the example here is that for a given architecture A, the numbers that you see are for a small mission of 6 crew versus a larger mission of 36 crew. 24 technologies have to be developed for the small one, but we don't need to develop 120 technologies for the mission that's 6 times larger. We only need to develop 30. The elements, number of elements, is 74 for the small missions, 1 to 3-5, but 525 for a 2-village mission with growth. And if you remember from the previous chart, 1 to 3-5 doesn't do 100% farming, doesn't do construction. So that's why you have many more elements for the larger mission. Headcount, operations cost. So compressing the size of the mission doesn't mean that you eliminate all the stuff that you need to run the mission on Earth. So we have big economies of scale there. And finally, launches are fairly proportional to the scale of the mission, even though we have this plus 63 term, which gives us some economies of scale. So with that, we can see an example at 3 mission scales. So what we see here is that for a 6-crew mission, design, development, test, and evaluation and operations account for almost half of the mission cost. Actually, more than half, because margin is proportional to everything. But as we scale up, we notice that that the cost per crew member, the life cycle cost per crew member, becomes just a fraction of the total mission cost. So this is the how economies of scale manifests in this model. We also see here that when we put it on a per crew member per year basis, so this is like a cost to have somebody on Mars for 10 years or 5 years. There are, again, significant differences from 1.7 billion per crew member per year for the 6 crew mission to down to 300 million for the 36 crew mission. So what we see with that is that we have economies of scale that amortize these fixed costs over more units as expected. So now with that, we can turn to economies of scale on the demand for crew time. And this part of the work has 3 key parts. It's defining the activities, it's the activity time equation, and then accounting for economies of scale. So we'll look at each of these in turn, starting with defining activities. So in my model, I have 533 unique activities. They're based on an original list of 484 activities developed by Dr. Stuster for his NASA project. And I amended and extended them with support from other members also of the Pale Red Dot team. And I've classified them here in 12 functional areas and in 6 time categories. So an example would be that activity 104 is in the habitat functional area and in the logistics time category. And its definition is to prepare a meal for crew consumption manually using surface habitat food cooking equipment. I'm looking around to see if anybody was at the Pale Red Dot analog mission, I think probably online. So this was a time-consuming activity for us. So yeah, the next part is the activity time equation. So what we have here is that the total time demanded for all 533 activities is the sum of the repetitions of the activity of each activity I times the number of crew needed by activity I times the total time per activity start and per crew member. And that is defined as a fixed component, which is a setup time for one instance of the activity, meaning when you start a certain activity, it's going to cause you to incur a certain fixed duration of time that has to be paid. And then the rest of the time in the activity, my abstraction is to say that the rest of the activity is made up of uniform tasks of the same length, and we have a number of those uniform tasks, and then we have a duration per task. So obviously this is not reality, but it's a nice abstraction, and it's probably good enough for what we want to do. And then the last term are productivity factors for specialization, task focus, and learning. And these can take a value of 1, more than 1, or less than 1. More than 1 would be a penalty because it increases the time demanded. Less than 1 is a bonus. So again, with our example, if B104 is number of times to start preparing a meal for a 5-year mission, then 5 years by 365 by 3, 5,475 meal preparation starts. So if we rearrange that equation and divide both sides by the product of crew size and the endurance, what we get is time demanded per crew member year or per crew member day, which is what we want to look at if we want to understand whether economies of scale are operating. Because what we want to see, are we saving time out of an individual crew member's day, right? So what we do with that is we rearrange so that we split up the setup component from the tasks component. And the setup component is the product of the number of starts times the number of crew times the engaged in the activity times the setup time per activity divided by this product that we saw before. And then the tasks time, the kind of variable cost of time per activity is the product of the activity starts. And let me just, and the number of repetitions of the task, the crew, and the duration of each task. So the number of repetitions of each task within the activity is M. So with that, we can look at an example. If we have the 5,475 starts of meal preparations for the 6 crew mission versus the 36 crew mission, we see how the 36 crew mission comes to 6.7 crew minutes per crew member per day for just the setup time. Now, that is regardless of the number of portions that are prepared. So my assumption here is that my two assumptions are that we need two crew to prepare the meal, and that preparing meals every time you start the activity, it's going to be a minimum of 20 minutes, regardless of how many portions you're making. Now, different people could argue with different numbers for these, but that's the point of modeling, that we transparently lay out the assumptions so that people can work on that and validate them. Then the next component, the product of the time needed for the variable part of the time, the 0.4 minutes means that we are assuming that every portion costs 0.4 minutes. So 6 portions for the small mission, 18 per village for the larger mission. We get this 2.4 minutes. The sum gives us the final total time per activity. So you can imagine that this is taking place within the model for all 533 activities. And in this way, when you configure it in this way, you have a high resolution model that can really tell you a nice estimate of whether you are getting benefits from economies of scale or not. Okay, so now that we have a nominal crew time with the effect of economies of scale baked in, we can turn to the treatment of productivity. So productivity, there are 3 types of effects: specialization, task focus, and learning. Now, in the interest of time, I've left out the derivation of these factors and calculations. It's in backup, and we'll just discuss an intuitive example. So something light to change the mood. So larger architectures have more specialists available to staff activities. And the issue here is that we have our comparison again, 4 crew versus 36. But we are on Mars to explore and to do science. So based on the way NASA does its architectures, typically there is always a traverse, or nearly always a traverse of 15 days. So people are in a rover and they're on a long-term trip in a camper, think of a camper van. So if 2 people are away from the small mission and 4 people are away from each village, so we're showing 2 villages on the right. So I'm showing 18 people, but that's 1 village. We have 2 villages. So you have 4 people per village away from the larger mission. Here's what happens. In the surface habitat at any one time, for the small mission, you have 2 crew, and they're wearing their 7 or 6 hats. And in the larger habitat, we have 14 crew at any one time. And because we have more crew, we can now afford to have them wear fewer hats. And this means that each person is more deeply specialized in what they do. It also means that we have more specialists of any one kind. For example, the blue hat stands for electrician. So, you need an electrician to change a light bulb in the habitat on Mars. You only have 1. So, bad luck if they're busy doing any of their other 6 things when you need to change the light bulb. But if you have the larger mission, you have 3 blue hats in the habitat at any given time per village. So 1 electrician versus 6. And the 6 are more deeply specialized. So that solves a lot of problems, and you can imagine that the larger mission will have benefits from specialization, more task focus, more learning. We can also imagine that the small one, they will have more looking up of unfamiliar procedures in manuals, more interruptions, more multitasking, reduced learning. So all of these things would have to be quantified somehow if we want our models to be more realistic than previous models. We're not claiming that this model is perfect, but at least it's a step forward. So now that we have realistic calculations for time per activity for all activities, we can calculate a range of performance metrics for architectures. So that brings us to the last step of the modeling and the approach, right? And here we calculate metrics for architectures over a broad range of mission scales. Now, a basic set of metrics is rolling up the time demanded by activities into categories such as logistics and utilization, the expression-related profession, the chefs, and growth, the miners and the tunneling people. So this is what a typical day would look like. And note that we use Earth days, not sols. On Mars, the duration is 24 hours and 39 minutes of 1 revolution. But we use Earth days for comparability with everything in the literature. But all the calculations work and the results are the same. So what do we have here? What that means is that in a typical average day for an average crew member, about 5.3 hours would be spent on logistics. We can convert that to full-time equivalent. And it's a very simple calculation. It's basically dividing the logistics time by the work week. And you get multiplying it by the number of crew, and you get the logistics FTE, LFTE. So the 36 crew architecture has 21 LFTEs, 21 logistics full-time equivalent people. Now, non-logistics FTE is simply the number of crew minus logistics FTE. So what that means is that you have 14 people who can add economic value on Mars, whether it is science, exploration, building permanent habitats, or just journalism, right? That adds value. So with that, we will now see how we can use these time-based and other model outputs to calculate a new metric, a novel metric, the Robustness Composite Indicator. So I defined complete robustness as the absence of vulnerabilities. It was a lot of thinking and back and forth to do that. But I came up with 15 different kinds of vulnerabilities. And just to help our eyes a little bit, I'm just going to zoom in on 3 here. And for example, the ratio of reserve FTE number 2 means how much time in reserve is available, which is not demanded by anything, divided by crew size. So, if you have none of that, then that's a weakness, because if things go wrong and you need more time, you have to not fix the life support system so you can fix the water system or something like that. So the architectures which exceed the upper bound receive a flag of 1, meaning like an A grade. And architectures which fall short of the lower bound get a -1. And then adding all of these together, we basically come up with a number, and then dividing it by the 15 vulnerabilities or strengths, we get a robustness composite indicator in the range of 0 to 1. So it's a normalized robustness composite indicator. Now, the model calculates this ROCI metric for all 17 architectures. This allows us to compare them for relative robustness. Okay, so what we see here is that the smallest 4-crew mission has more vulnerabilities than strengths. And we can see that there is no social diversity, no time for self-expression, not enough physicians. They use up all their radiation budget. They don't have a self-rescue capability, no reserves, not enough people to support all their systems. So, but what we see, which is promising, is that it gets better with size. So as the size of the architecture grows, as we go from 4 crew to 21 crew, we see the robustness score improving. And we get close to the best possible score under this modeling approach with the largest 21 crew, 1 village architecture. The -1 is because they don't have the self-rescue capability. So moving to the 2 village architectures, we see that the larger ones are more robust. So what is interesting here is that the smallest architectures that achieve the perfect score are the 36 and 42 crew dual village architectures. And for 3 villages, same pattern. But the interesting thing here is that, we don't need to go, if the thing we care about the most is robustness, relative robustness, we don't need to go to the expense of 3 villages with 63 crew. We can get the same robustness with 2 villages and 36 or 42 crew. So we've seen how to account for economies of scale in cost and time. We've seen the relative robustness of architectures. I skipped the relative autocatalytic potential in the interest of time, but now we can use all these tools that we get from our models to compare different architectures and to see, what we should do. Should we go small or should we go large? And if large, how large? So the results. So the first result here is a traditional benefit versus cost trade space. On the horizontal axis, we have the life cycle cost of architectures. On the vertical axis is crew years of NLFTs, of non-logistics FTEs. So all the value-adding FTEs. And each dot here is an architecture. And then the markers of the architectures show its relative robustness. So the gray X's are the least robust architectures with ROCIs under 60%. And the filled in green diamonds are the most robust architectures with the high scores over 90%. And we note a few things. First, robustness correlates with scale, which tends to support the second hypothesis that larger is more robust. We also note that on the benefit on the vertical axis, again, we have a correlation with scale. So we can see that from the number of villages and the number of crew that the biggest mission is the highest benefit and the smallest mission is the lowest and so on. So that's a good step towards supporting the first hypothesis, but benefit is not value. So we will have to work on that a little bit. Now, we eliminate the smallest missions due to low value and the low ROCI, and the largest due to high cost. And this leaves for robust architectures that are interesting to study further. Now, but we can also use the model to investigate value-related metrics versus mission scale. And we do that by plotting a specific cost similar to something that we saw in the very beginning with the NASA architectures. So on the vertical axis, we have cost in millions of dollars per NLFT crew on Mars per year. Think of it as the economic cost of putting a scientist or an explorer on Mars, right? This is the annual full economic cost of having somebody on Mars to perform services. And on the horizontal axis, the number of launches is a proxy for scale. So mission scale. So we have mission scale against a value-related metric, which is cost effectiveness metric. What's going on here? Well, we see that the smallest NASA architecture, NASA-like architecture for crew for 5 years would mean a cost of almost 10 billion per explorer on Mars per year. And the larger architectures bring that down to around 650 million. So significant differences. And this supports the weak form of the first hypothesis that the larger architectures are more cost-effective than smaller ones. Now, this trade space exploration exercise allows us to focus on a smaller subset and study these down-selected architectures. And what we have here is 3 two-village architectures, 30 crew, 36 and 42, and a 3-village 45 crew architecture. They all have growth capabilities. They are for a duration between 9 and 10 years, and the number of sites is from 2 to 3. The width of the bar is actually the length of the work week. So you can use that to see, to judge, which ones make the crew work harder. The numbers that you see here are FTEs, full-time equivalents. So architecture 26310G has 8 utilization FTEs, meaning scientists/explorers, 21.8 logistics. Total is 36, and it's well balanced like all the others because it includes time for growth and time for self-expression. So, okay, let's do a quiz here. Why is 26310G bolded? Any thoughts? Don't answer, I will answer. So, it's because it won the 2023 NASA Rascal first place overall and best in theme Homesteading Mars Awards. And, this wouldn't have been possible without a few of the people are here in the room and I'm sure online as well. And this was the product of the hard work of a large team of 25 students here at MIT. I'm really indebted to them for all the hard work that was done. And, we had, and we are also indebted to NASA and the National Institute of Aerospace in Rascal for really this amazing opportunity to exercise our engineering, skills such as they are. So apparently we convinced the judges that pale red dot was not just a good architecture, but that it was also affordable, right? Because, I mean, first place, so, if we had a weakness, we wouldn't have one, right? Well, peak annual funding of $7 billion for the candidate Mars architecture pale red dot is in line with current deep space exploration budgets, suggesting cost feasibility. So the peak is about a little bit short of 7 billion in the mid-2030s. The average is 3.1 billion. And both of these play along well with the current deep space exploration budget. The Government Accountability Office pegged it at 6.7 billion in 2022. So that's without including the 4 billion for the ISS. So there is cost realism here. I mean, this mission architecture could be supported by NASA. But here's the thing. NASA doesn't have to pay for all of it. I found a very unexpected result while modeling the cost to each Artemis Accords country. So for those who are not familiar, Artemis Accords is a framework for bilateral agreements between NASA, the United States, and allies who agree on a common set of principles for exploring the moon and deep space. And I was looking for, what was it going to cost each Artemis Accords member to pay to send one of their, nationals on the Mars mission that is led by NASA. And here's what I found. So as crew size and endurance increase, the lifecycle cost per crew member per program year falls, making the Mars mission affordable to more Artemis Accords members while keeping the annual cost to NASA low. So what's happening here? The actual budget that is addressable increases as you make the mission larger because the subscription cost comes down and it comes down again. And, from 600 million or change for the smallest mission, the subscription cost, the ticket for a country to send one of their astronauts to Mars comes down to 111 million. And then we go from having three countries on Mars with a 4-crew mission to up to 21 countries on Mars. And that is a game changer. That is what actually supports the strong form of the value hypothesis, because now we're talking of value in absolute terms, that NASA pays the same cost roughly, whether it is doing a 4-crew mission or 6 or 12 or 36, give or take, these are all the same number because of the error bars here. But what NASA gets, they get much more science with the 36-crew mission. They get much more robustness. We've seen that. And so because they pay the same and they get more value. So we have also found support for the strong form of the value hypothesis. We get value in absolute terms, not just in per crew member terms. So if I could redo the pale red dot mission patch, because we had a very talented artist in the analog mission who created a mission patch, but if I were to do my own, I would certainly include go big or stay home on the mission patch. Again, this is the work of all our talented team members. So Ezra and Francesco contributed work for designing these field hospitals, and Madeline, Mars Mission Control Centers, this was all Francesco. The maker spaces, Francesco, Cormac, Palak. So the maker spaces, 480 square meters per village of machine shops. So MIT thinks they have machine shops. Wait until you see what we'll have on Mars. And then the swimming pool and the bar. Trying to remember here. Lenny, help me. Was Estelle?
I think Estelle and Madeline's idea for the pool.
Yes, yeah.
Radiation shielding.
Thank you. Yes. So the idea here is that the pool is pool of radiance. I don't know. Tell me later who understood the Easter egg here. Is on top of the bar, which is the 10 forward bar. Another Easter egg. We will see who dates themselves with these. So yeah, go big or stay home. Conclusion. Well, scale is, I think one big finding here is the appreciation that scale is more than a cost driver. Scale really should be fit for purpose especially in hostile environments. And we see here from the example, 1 century apart, the real Scott and the real Amundsen raced to the South Pole, the pioneers. Because it was a race, they designed small so that they could win the race. But they also cut it close and took risks. And the risk that Scott took, which didn't work out, was that he calculated very carefully with all the data available, the weather patterns. And then on their return, the weather was unseasonably cold. I mean, I think just like now, I guess, or actually this weekend. So, and so we have the picture here of the tomb of Captain Scott, unfortunately. But then 100 years forward, and look at the size of the, these people with the red parkas for scale. This is just a small part of the Amundsen Scott South Pole Station. One of our colleagues, Manway, was there, I think, for a few months. Yeah, I don't know if Manway is online and maybe he can tell us something, but I think he's traveling to Tasmania right now. So anyway, so 150 people in the summers, 40 people in the winter, and they don't feel that their safety is under threat. Everything is provided for. Huge logistics. There are arches with, just like the Indiana Jones movie, with all the crates that are stored, the arches with all the logistics and everything. It's incredible. So you need scale to underwrite the robustness and success of a dangerous high stakes venture, like sending people on their own, millions of miles away to Mars. And with that, just to wrap up the key takeaways and the contributions. So the first key takeaway is that I believe that NASA and its international and commercial partners would really benefit from a comprehensive study of a large mission to Mars. It's a study, it doesn't cost much, it's a study. We're not building anything yet. The second key takeaway is that I propose a paradigm shift for human spaceflight from Earth to orbit mass, which has been paradigm until now, to crew time. Because mass would just send more of it with a reusable spacecraft. But crew time, now you have to expand the whole architecture if you want to have more crew who don't fit in what you have already. So that is more inelastic. The elasticity of supply of crew time is much less than mass. In English, crew time is the scarce resource. Mass is not going to be the scarce resource. So the contribution in this thesis, methodological ability to evaluate architectures across a broad range of crew size and endurance, using crew size, endurance, and number of sites to drive design, the high resolution crew time modeling, the new metrics for robustness, growth, cost effectiveness. And then domain contributions, obviously the payload Mars reference architecture, which is actually my product, but also our team of 25 students is a contribution. In the thesis, I have a list of 153 under-resourced crew time statements in an appendix. So this is the work of Mars architects over decades. Wherever they mention something that has crew time implications, but nobody actually quantified that, I extracted it. So that's there, and it's now a resource that can be used to improve crew time modeling. And finally, another resource for modeling, the parameters for the crew time model can be the foundations of analog studies. So we can design analog studies to test the parameters that I assumed, and we can therefore improve the fidelity and the skill of the model. Now, future work, so potentially opportunities to go into evolutionary architecting, like what would it be like to go from smaller to medium to larger missions? The design of experiments to improve the fidelity of the parameters, as just discussed, and the discovery of more vulnerabilities and the incorporation into the robustness metric. I think that can never end. Discovering more vulnerabilities, I think we can just keep finding them. And then possible applications, architecting the first Mars mission, lunar missions. We can generalize this FT and ROCI approach to defense applications. So I'm thinking of the littoral combat ship right now. So, maybe if they had done that first. And then national and geopolitical posture. So using these metrics, we could have a subscription price for an international Artemis Accords mission to Mars, which could then make Mars happen. So, and that's the end of my presentation. I wanted to acknowledge and thank especially my thesis advisor, Oli, for believing in me and taking me on as his student, and everyone, my thesis committee, for all their wisdom and guidance, and my colleagues, too many to name here, but I think I name everyone in thesis, for all the work that we did together. The SDM program, for everything I learned and all the opportunities I had as a lead teaching assistant there. The Department of Aeronautics and Astronautics, the leadership and staff, always supporting my research, my projects in large and small ways. My funding sponsors over the years, the community who have accepted me, as Oli said, I came from a very different background, and the community accepted me and valued my thoughts, and I thought that was amazing. And finally, to my friends and family who supported my journey all these years. And in closing, I just wanted to again come back to all the amazing collaborations I've had with students here, fellow students here. And these are on the left are the results of all that work. And those results are team results. And they were earned equally by every student who participated. On the right, I have some selected publications. These are in different domains like the moon, low Earth orbit, also complete architectures to reconfigurable robots. But they're all related in some way to the question of what is a good architecture. So with that, thank you very much. I think I've run over by a minute. I apologize for that. And thank you.
Okay, great. Thanks, George. We'll start with the Q&A. We'll start with the committee. Maybe, how about we start with somebody online? You guys are still with us. So faculty, committee, readers, please go ahead. Dan Hastings.
Yeah, so George, thank you very much. That was a very interesting presentation. And certainly on the basis of what I'm following it seemed to make a lot of sense. You showed the South Pole station right at the end. Of course, they didn't arrive at those numbers just out of the blue, right? I mean, as you said, during their winter, they have about 40 people a year there, and they can't bring in anything. The only thing they can use from the environment is water. Everything else gets brought in, and they're isolated. So if you applied the same methodology, would you come up with the number 40 for them as well? And since, of course, they didn't, that station you see there didn't just appear there. It was actually built up over time. If you look historically, there was a time when it was actually much smaller than that.
Mm-hmm.
If you actually followed that, were they actually trending towards what you actually have come up with? It takes a certain scale to live and to do the work, because they have to do science there as well as exist. I mean, if you looked at that, and looked at their path to it, what conclusions might you actually come to?
So thank you. I think that's an excellent question for future research as well, Dan. I did not actually attempt to reverse engineer it, but what I did do, I did validate the outcomes of the model against parts of things that happen at South Pole Station. So for example, they have a South Pole food growth chamber. It has an acronym too long to remember. There is data for the time that it takes to grow food at the South Pole Station. I used that data and compared it against the outcomes of the model that I built. So I did this validation exercise at this smaller scale than with respect to South Pole Station. But I agree, it's fantastic future work to actually trace through the evolution of how it grew, because the history is all there and it's very well documented.
Okay. And the other question I had is, nowhere did I hear you use the word learning. And I would have thought building up all those modules and doing things repetitively that people would learn over time and get more efficient, right?
Yes. So learning is included in the model. As you saw, I ran over by a minute. If I had also tried to talk about learning, would have been in big trouble. But let me show you.
And all of the extra time you didn't take. Okay.
Yeah, being strategic about time. 1 second, I will find it. Right here. Here. 1 second. Yeah, here we go. Okay, so I use the experience curve method where, yep. So as I track the cumulative tasks in each functional category, and then there is an abstraction here that I lumped together tasks that might not actually be similar, but I said, well, let's say they're similar enough. And I compensated by being very conservative of only 0.5% per doubling. So the very best case of learning is saving time by only about 80%. So if the learning factor comes to 0.92. So I was very conservative with using learning. I mean, I developed the method, but because the approach to use the constants for learning was actually very approximate, I didn't go overboard with it.
Okay, great. Thank you.
Thank you. Thank you for the question.
Okay, maybe we'll just go back and forth.
I've got one follow-up on the South Pole.
Yes.
You talked about the additional robustness you get from having 2 settlements versus 1.
Right.
What would be the difference in the situation in Antarctica compared to Mars that would, I mean, are they doing the right thing by having just 1 big station?
I mean, it's
Transportation, of course, is very different.
I mean, I've looked at the layouts, and it's almost like it's 2 which are connected by 1. But it's, I mean, the probability of a catastrophic, event is very low. You could always say, let's be safe by having a second one. But I guess one difference between the South Pole and Mars is that on Mars, they are on their own for 2 years. Here there are options. I mean, normally no flights in the winter, but there are ways to rescue people if needed and so on. So
That's what I was thinking. The
Yeah,
transportation makes it.
right.
maybe
So
makes it
an architect would take all this into account, including cost, and then make a judgment. In the case of Mars, I think I started with, we're putting these people on their own for 2 years or more. So let's start with making robustness a constraint, and let's see where the cost ends up.
You happy?
Mhm.
Okay. Dr. Siddiqui?
Thank you, George. I really enjoyed this presentation. You've done an amazing amount of work, which is really great to see. So I guess my question is related to what I have mentioned in my comments, and I would love to get your thoughts. You showed some very interesting charts, showing comparison of different scales of the mission sizes, right, along with their value. So I think there was a slide 37, 36, where you show, sort of the how they compare. And sort of as somebody who cares always about the knee in the curve, so to speak, right? I'm always interested in where's the knee in the curve, where you can begin to see a clear difference in the marginal benefits. Walk us through how you think of the knee in the curve, because clearly there are some very relatively small architectures right at the knee, right? 8 crew members or 7 crew members and so forth. Which I would assume would then be much lower in total costs as compared to some of the bigger architectures. I do see your argument for robustness, and I think that's important. But in my view, total cost will always remain an important metric that sponsors will be looking at. So walk us through this.
Sure. So the concept exploration refinement study, where you refer to this knee where there are architectures with 5 and 6, etc. That was talking about specific situations of the crew. For example, if there is 1 crew member incapacitated will you still be able to carry out the science mission, and how much of it will you be able to carry out? What about if an EVA pair is incapacitated? So that was a specific look at a scenario, and that was the way they looked at robustness. It was not a holistic look at robustness. Was it? They were asking, is it robust to the incapacitation? Is science robust to the incapacitation of the crew member? Now, with this diagram in particular, the way I look at this is that it's a three-dimensional trade space because we have the different categorizations of robustness. And so what looks like the knee isn't necessarily the attractive place that you want to be at. What you want to do is you want to be on the frontier, and you want to be the lowest. I agree with you completely. Absolute cost is a very important metric, total cost. And so 2539G is very interesting because it has a lower absolute cost than 2631G, which is equally robust, but has slightly more benefit in more crew years. And so that's how I think of these. But because there are so many assumptions and estimates, you don't just take one architecture to carry it forward, you take a few and you continue looking at them.
Sure. No, I hear what you're saying, that it's more than a two-dimensional plot, and if you bring it into three dimensionals, then the features, so to speak, of the trade space might begin to look a little different. So just a quick follow-on question related to the cost aspect, connecting to the comment you just made, George. Towards the end, you're making an interesting argument about this, right? About bringing in international partnerships and then sharing in the cost burden. So on one hand, I'm absolutely committed to fostering international partnerships. This is something I really care about personally, but practically, seeing the state of international partnerships is a very different situation altogether. The experiences on ISS, tensions between Russia and US today and into the future. When we ask for dependencies in terms of budget, very real budget that would enable such a mission, what are your thoughts if some decision maker were to push you on this?
Well, so here's the thing: the bigger you make the mission, the more flexibility you have as the lead sponsor. So NASA has the more flexibility to find ways to close the funding, right? So if, for example, I'm looking for a specific chart. Here it is. Right. So here is what happens. The yellow line of it is the life cycle cost per crew member per program year. So program year means the 27 years, right, that you need to run the program. So this is roughly the average cost, the average subscription price that everybody has to contribute. So as the mission size gets bigger, and I ordered all the architectures by number of crew, strictly by number of crew. As the mission size gets bigger, the entry price becomes smaller. As the entry price becomes smaller, the total budgetary capacity increases. So I don't know, the colors here on our screen are a bit faded, but I'll try and trace it with the mouse in case. So this is the total budgetary capacity, and it increases from less than 7.5 billion, order of 10 billion, because when you reduce the price, it's now accessible to more of the 33 Artemis Accords countries. So there is more total budget as the cost per crew member comes down. Now, what that means is that if you take the 6.7 billion deep space exploration budget that NASA has, and if we leverage the other Artemis Accords countries to keep the cost to NASA under $1 billion, NASA still has room, has dry firepower, powder to pick up the slack if they cannot get enough subscriptions, from the other Artemis Accords members. And it also shows that choosing the 36 crew size was a good idea, because we still have flexibilities there, because there is still unused budgetary capacity, not just in NASA, but also in the Artemis Accords countries. So that, to answer your question, Afrin, I'm not in this thesis. I'm not addressing the realities of international relations and the difficulties. But as an architect, I'm trying to create, as an architect of an enterprise, so to speak, I'm trying to create something that maximizes the chance of the State Department of pulling off a deal. Let's put it this way, right? That's all I can do. I cannot go beyond that.
Great, thank you. Thank you.
All right. Number two. V.
So thank you very much, George. I really appreciate the way you've, in a very basic way, rethought the concept of what was being planned. And I always appreciate people who sort of think outside the box as you really have done. And it's a very interesting output. So my particular question is, because I'm at one level saying it's nice to have more people available for science, but it's also a question about, well, how much do we really want to spend on science? I mean, I love science, but I also like hospitals and schools and things like that.
Right.
So you're basically, almost the first thing you said was that humans are 100 times more efficient than machines in terms of doing science. Well, certainly that's been true for a long time, but as we think about the capabilities of robots of various sorts, that's probably not as true anymore. So could you share with us a little bit to say, well, maybe that isn't that true, and maybe would there be more investment in terms of doing science in the robots as opposed to having people that you need to feed and entertain and all this kind of thing?
Sure. So I look at this in a couple of ways. So the first step is, if the goal is only science, and if you don't want to put humans in harm's way, we can continue doing what we have been doing and leverage, as you said, all the advances in robotics, artificial intelligence, and everything to try and accelerate the return of science from robots. Now, once you've decided that for some reason you want to put humans, and those reasons usually are a package of reasons, it's not just science. So it's national posture, it's the human spirit, it's the feeling that humanity is now on another planet. People value that. Some people value that. So once you decide that you want to put humans on Mars, now you have to have a situation where humans look after machines and the machines look after the humans. So once you go into that and start designing that, the argument could be made, as you said, that machines are improving. So yeah, let's have more machines and fewer humans. But what is motivating wanting to have fewer humans? Is it because of cost? Are we trying to save cost? And at what point are we making the mission brittle and vulnerable, right? I mean, over-dependence on machines, you're always, machines don't have in this very high number of degrees of freedom that humans have to deal with unexpected states of the system, of the socio-technical system. Humans have that. So, I am all for automating everything, as long as the humans get to be, journalists and chefs. And so similar argument to the universal basic income. A capitalist would say, let's replace all the workers by machines. But then, somebody who takes a more holistic perspective would say, well, we need to find something meaningful for the humans to do. So we don't want to replace all the humans by machines. So I'm thinking about it in all these ways. I don't have complete answers to that. I certainly think it's future work for another student to look at the trade-offs between robots, AIs, and humans. But I have not looked at that. I thought that if I want to have the absolute best robustness, I should be designing with humans and for humans.
But let's see, we have some additional committee members online. Dave Klaus, Professor Klaus in Colorado, maybe, and then Bob Shishko. Yeah.
Sure, I'll go next, Ollie. So George, first of all, I wanted to say I really appreciated your very thorough proposal and analysis for this lifetime embodied energy concept. And I'm a huge advocate of sending large fleets to Mars as a means of increasing robustness and improving the productivity. So it's great to see your approach at trying to quantify that. It makes common sense. I think it makes sense rather that it should get more efficient with more people going up to a point. So I have two basic questions. I've been trying to take notes, listening to your presentation and reading through the dissertation. First question is in the dissertation, actually both of my questions follow up almost on the previous two speakers as well, or two questions. In the dissertation, you mentioned robotics and AI, in addition to potential other technology advancements, as possible limitations to your strategy. So I want to ask you, since I can't pick it apart, what are the major disruptors that you can envision that might derail this proposed autocatalytic approach? In terms of, what do you think are the big hurdles here?
Sorry, clarification on that. Are you asking derail the methodology or derail the actual architecture?
The actual approach, not the methodology, but what are the hurdles here? Aside from World War III breaking out or something, what are the potential roadblocks that would keep NASA, or I can see a response of, well, this is a great idea, but what's the major potential concern you would have with implementing something like this?
There are several, realistic concerns that would have to be addressed, and we can maybe talk about a couple just in the interest of time. So one would be that the current NASA budget is stretched thin across many different interests and stakeholders, and it would be very difficult to find the 1 billion or less that this chart actually showing right now. If we assume that Artemis Accords members sign up and they each pay their 111 million per crew member, and Japan also has Toyota build a rover with its 444 million per year, and if we assume that all that happens, we still have the problem that NASA has already committed all its deep space exploration budget to other things. So I don't need to name the systems, but we all know them. So that would be a real big hurdle, because stakeholders don't like to change these things. I would say that's probably the number one. I think the second one would probably be inertia and conservativeness of doing the thing that has been done. So we've done ISS exploration in a certain way. It is really tempting, and I can see the perspective of fellow architects that we should do something similar of that size, because we know how it's done. To actually implement this, you'd have to start over with a different set of philosophies for nearly everything. You'd have to design all the technologies for manufacturability instead of reliability, for example, because you have this big makerspace backing you up. And then at the system level, manufacturability will turn out to be more important. But good luck convincing everybody of that, I think, right? To give up the heritage of all the technologies on the ISS, which are low manufacturability. So those were the two I would pick. There's more, I think, but thank you for the question.
Okay, thank you. Yeah, it's interesting because you're trying to change the status quo, and that's always a challenge. I wasn't thinking so much about the budget in the sense of what's already planned, but just in terms of trying to actually implement this. My other question is a little more practical, and I apologize. I may have missed this in your dissertation. I was trying to read through there and find the numbers that you used, but the Mars Perseverance rover in 2021 had an estimated cost of about $2.1 million per kilogram to the surface. So without vetting all the assumptions in your model, with a 7 billion peak annual cost proposed, I think you showed at one point, that's only about 3,300 kilograms to the surface at today's launch cost. What's the necessary dollar per kilogram that you would have to have in there to support your proposed budget numbers?
So for 100 tons to Mars, we need 9 launches of a reusable Starship class system. I baselined each launch at an expected value of 25 million per launch with a log normal distribution, because I didn't mention it because of time, but all this is run within a Monte Carlo model. So all my costs are log normal distributions with the fat tail towards cost overruns. And the 25 million per launch times 9, let's just call it 10 for easy, 250 million, puts 100 tons on Mars. So 250 million, 100 tons on Mars. Sorry, difficult to do math in my head right now.
Okay, so you're expecting then a, you know, a couple order of magnitude decrease in the actual cost.
I think that's yeah, I think it's doable. I mean, if you look at cost per launch for Falcon 9, we're not that far from the 25 million cost per launch of a Starship class system. We're not that far. So, you know, I think it's doable. And Starship is fully reusable. Falcon 9 is, the upper stage is single use. So,
Of course, you know, getting to Mars also implies the transit and the landing costs for fuel as well. But anyway, there's definitely a lot of room for improvement in terms of the launch mass capabilities that would make this more efficient. Okay, I don't have any more general questions at this point.
Let's go to, thank you, Professor Klaus. Let's go to Dr. Shishko, JPL.
Well, you know, we certainly see that having read the whole thesis, George has just put together a lot of very valuable results that, you know, are worth taking a deeper look at. And this presentation compresses a lot of work into a 1-hour presentation. It's a well-done job. But I did make some notes, and unfortunately, the disadvantage of going last is that most of the thunder has been already taken up by Afreen and David. But I did make some notes. I said that, you know, NASA, you know, might come back and say, even though you've shown that the life cycle cost per non-logistics FTE per year is certainly is certainly higher. Sorry, is certainly this showing a decreasing average as the size of the number of crew people expands, and that the marginal is also decreasing. But NASA might say that the life cycle cost must be, you know, must fit into an affordability criteria or condition. And this is something that NASA is very reluctant, in my experience, to deal with. If you recall, back in the Space Exploration Initiative around 1990, there were a number of 500 billion leaked out, and that kind of put a damper on the whole thing. So what I'd like to think might be a next step is for NASA to do what's called an ICE, independent cost estimate, taking the same architectures and having you know, have them run their models and see what they come up with in terms of whether they get the same result or a different result. I think that would be something that NASA should perhaps think about undertaking. So you know, affordability is the sort of thing that is, you know, going to be an important consideration, and I think that's been recognized by both David and Afreen. But again, it's a tremendous amount of work that's going behind this, and congratulations, George.
Thank you, Bob. Thank you very much. So just on affordability, I think we've covered it, but I wanted to just mention one more thing, that the model is set up to automatically calculate sand charts for every architecture. So this is for the particular pale red dot architecture, but this can be done for every architecture. It's also, all the numbers are Monte Carlo as well. So, you know, you can do distributions on these numbers. And when I built these charts here, I used the P95 value from the Monte Carlo output, meaning that there is a probability that the life cycle cost per crew member per program year, there's a 95% probability that it will be 584 million or less for the 4-crew mission, and 95% that it will be 111 million or less. So because affordability is such a huge concern, I thought it was important to model the possibility, the likelihood, and not possibility, the likelihood of cost overruns, and then to see where the numbers shake out. So that's all I wanted to add. I think affordability, you know, you see here what's going on. 2 NASA astronauts with the 4-crew mission, 8 NASA astronauts with the 36-crew mission. So the leading role of NASA is reflected in the composition, but the 8 is only 4 times more than the 2. And the 111 is like 5 or 6 times less than the 584. So it's actually cheaper in absolute terms for NASA to, per year to pay, for the larger project, at least, in the first 18 years. After that, the small mission stops, but, 18 years is, in the long run, we're all kings, right? Okay.
Is Dr. Wooster on from SpaceX?
Paul, sure. He did send his feedback. So,
Okay.
Yeah.
So I guess we'll open it up for everyone. Anybody other questions?
Well,
Second round.
Could I make one comment? This is following on with Richard's question about the use of robotics. It strikes me that your methodology could actually be used to address that problem directly. By doing, like you did a detailed task analysis for people, you do a task analysis, all the things the robots have to do, and then you can compare, like the way we operate Perseverance from the Earth, where it takes hundreds of people, you have a minimum turnaround of 2 days. You have to be really conservative because if it gets stuck in the sand and so on, and compare that to what you could accomplish with the same rover.
Yeah.
If you had somebody on Mars who could operate it in real time.
It's true.
And dig it out from the sand if it gets stuck, and replace instruments so that you didn't have to have a new rover every time.
Yeah. And would have to add a new set of vulnerability indicators so that we can calculate the ROCI metrics for the two. Yeah. I think that's very promising. It's excellent future work. I hope somebody will do it, somebody who's listening. There is also a hand online. Chris Jones from NASA Langley is raising a hand.
Yeah, George, again, congratulations here. I think you've made some really impressive advancements here in the methodology of how we even think about architecting missions to Mars in a way that just opens up that possibility space very broadly and with a lot of great detail behind it. I'm particularly interested in the ROCI, the Robustness Index that you put together, because I think that's an interesting way to try and assess a lot of different figures of merit and compress that into something that's tractable to look at. And as you talked through that, I sort of saw 2 assumptions that stood out to me. One, that you looked at each of your metrics and kind of gave it a binary flag of a positive one or a negative one. And then in summing all of those together, it sort of assumes a fungibility across all of those metrics. So if you were to continue building on this method going forward, would you want to look at those assumptions in greater detail? And if so, in what ways, in terms of both the compression to a binary flag and then the fungibility across all the metrics?
Chris, I think both are excellent observations and excellent paths forward for future work. What I thought was that I wanted to keep it simple with the minimum number of new assumptions because I was creating something new. And that's why, for example, I didn't try to go into assigning weights or anything like that to the different flags. Definitely, as I said before, there's a big, open field of opportunity here to more carefully define these robustness, the different indicators here that go together into this metric, and also to expand the list. I think it gets better the more you work at it and improve it, because at the end of the day, it's a relative robustness indicator. It's not meant to be an absolute scale in any shape or form, but within the same set of assumptions, the same context, the same model, it definitely tells you something about the relative robustness of architectures. I agree with you. I think there is a lot of opportunity there.
All right, great, thank you.
If I'll just follow up, my only question was on thresholding.
Yeah.
Right? You
Mhm.
to earn a +1 or
Right.
-1 on the
Right.
ROCI,
Right.
there's some thresholding assumptions you made that could also be challenged, right?
It
Or-
can certainly be challenged. I mean, one thing I did is in the appendices to my thesis, I have included, so the body of the thesis is 200 pages and the appendices are longer than the body. So I've laid out every single assumption and every parameter because the whole point of opening up an opportunity for future work with large analog missions, where we can run hundreds of these small experiments and quickly knock off, validation or invalidation of many of the assumptions. I was more interested in plausibility and demonstrating a new methodology. Brian, sorry, we kept you
George,
waiting.
congratulations and thanks for interesting. Clearly, scale has advantages, but it also has disadvantages.
Yes.
And I'm obligated to ask you about your underlying activity model.
Yes.
And to bring up Brooks' law, amongst other things. So at the task level, if we go from a well-understood fixed duration task in an individual
Yep.
as a nominal basis, let me ask, clearly as we get to more and more people, then we begin to have coordination effects, and especially in the village you described, cross-cultural
Mhm.
coordination effects,
yeah.
which can be significant.
Yes.
So of the following phenomenon, which ones are you currently handling and which ones do you think you should begin to handle in your underlying activity model? One is just understanding the nature of the task by scope. So if I have 2 or 3 people working concurrently, how does it affect duration and outcomes? But then about whether or not you're handling rework mistakes.
Yeah.
And effects. So what do you think? Where does the maturity of the
So-
current activity model, where could it go?
Right. So I tried to start with abstractions that include certainly rework in the task focus penalty. So the way that works is actually I have something I can show. It's not specifically about rework, but the literature review showed that there is a lot of. Let me see, am I looking at the right thing? This is the one. So, so if you remember those factors, GSP, GTF, task focus, and GEC for the experience curve. So there is one of each for specialization, task focus, and learning. I include the rework within task focus. So if you're being distracted because you're multitasking, if you're being distracted because somebody is interrupting you to ask a question, so all these things affect task focus, increase the probability of errors. And the way I did it, this was very approximate and very low fidelity way. I basically said that, when we have the smallest missions and the number of hats, is 7, we'll have a lot more of that, of all the multitasking and interruptions and the rework and errors and so forth. So when you have errors, you have to do it again. That's wasted time. So in that sense, that's why this looks like that. That's why it's rising as you get to the smaller sizes. The red curve is the focus curve. And what that means is because it's a multiplier of nominal time, anything above 100 is a penalty, right? So the smallest missions have a heavy penalty for loss of focus. And I've lumped together everything.
I think where this could be challenged is and improved over time.
Oh, yeah,
is clearly there's a U here, not a slope, right? And what are the forces that affect that on the outer side, and how might the architecture of the society actually be considered with regard to that?
Well, so the reason I will defend what I have. Here we go. So I will defend it. So there are going to be problems at all mission scales that are not within the scope of this thesis, right? So at the smallest end, seeing the same people for 2 years. I mean, there's actually a quote from a Soviet cosmonaut that all the conditions for murder are met if you put 2 people in a camper van for 2 months. We're talking about a camper van for 2 years, not 2 months. So, the smaller missions might have their problems, larger missions might have their own particular different problems. What I'm saying is, I'm assuming that we have many, many more degrees of freedom and resources that are available to mission managers with a larger mission than with a small one to actually address these problems. For example, with the 2 villages, if you don't like, the people you're living with, You can go to the other bit. The thesis doesn't cover much of what you said. It's future work for other people.
I look forward to
Yeah.
doing that together.
Thank you.
I mean, we know for companies, right, for large firms that there's probably, you can be too big, right? And your productivity.
What's interesting is I think, this magic number 36. I mean, it kind of what begins to happen, clearly these effects begin to kick in, so.
Good.
Apparently
Okay.
the magic number is 42, but
I'm looking at the clock,
Yes.
and we do want to try and finish within 2 hours. So maybe we'll say one more question.
Hey, Ollie, this is Pat Troutman. Got a question for you, George. On your future work chart, you talked about the first Mars mission and finding a future state, which could be something like pale red dot. And NASA is actually going through the exercise of determining that future state and how that would drive that first Mars mission, as opposed to where we were 4 years ago, where it was basically a race to Mars with minimum cost. Given that context, can you go back to your cost chart for pale red dot?
Which one of the many?
It was the aggregate cost for getting to your chosen architecture.
Okay, let me see if I understood what that is. So this is one of them.
No, it had the dollar amount on the bottom, and it's like 2 charts further.
2 charts further. Okay. Oh, yeah, I got it. Yeah, this one. Yeah.
No, it wasn't that one. It was it actually showed how much it would cost over time to get to pale red dot. It was your aggregate cost chart.
Oh, the sand chart. This one.
Sand chart. Yes. Sorry. Okay. So help me out here. It says first crew launches, including refueling. Where are boots on Mars on this chart?
2039.
2039. Okay. So that's all up to 2039. So the first crew launches, and when are all 33 or 42 people there?
So they all go together into two crews. So the 36 people go in 2 flights, so 18 per flight. So they are there. They start developing the tunnels, and then the second crew comes before the first crew departs, and that's why you see this bump in the mid 2040s. This is the arrival of the second crew. The first crew moves into the permanent habitats in the tunnels, and the second crew in the connected, the old villages. So
that answers my question, because I wanted to know if this was a steady buildup of capability or sort of all at once. Because architectures that require everything to happen all at once are tended to look a little less favorably because there's not an early win, right?
Yeah.
So the other question I have for you is this sequence of cost and spending take into account the actual 2 years Mars missions and the ability of SpaceX to tanker up and everything in a small 1 month long window every 2 years?
Yes, I don't have the chart here. It's in the thesis, but I did calculate the sort of sustained launch rate, and the peak launch rate is 14 per month. At worst. I mean, you could Monte Carlo that, but it's roughly that. Yeah. And yeah, we've had feedback that this could be plausible. Yeah.
Okay, thank you. All right, those are my questions.
So Pat, good to hear from you again. So I mentioned, as you heard, an independent cost estimate. Is that something, well, first of all, we worked with JSC Code XB for a long time on trying to get them to do a lunar and Mars sand chart. I don't know where that stands now, but is NASA doing anything to implement a more detailed costing of an architecture?
Yeah, we're always looking at potential future architectures. The problem we have right now is that, as George mentioned, is that they opened up the objectives this year. We went from 2 crew to the surface for 30 days to whatever. And the reason why we actually had this homesteading Mars theme in the student competition was one of the whatevers was, hey, a nice line in the sand might be where those people at Mars are basically logistically independent from planet Earth with, small dumps of really high tech stuff. So it's imagining a new future state working backwards to that, to what that first mission would be. And those are the people actually from NASA that are on this telecon. They're charged with trying to shepherd that process of figuring out what that first mission should be. But before you do that, you have to figure out what your target state's going to be. So that stuff's all the iteration. So right now we don't have anything to cost. A question that was brought up later is more important. Would you cost that assuming certain pieces of very expensive NASA infrastructure, or would you cost it in a more optimal way where you didn't have to use that infrastructure? And that's a political question. So yes,
Exactly.
we're thinking about it tremendously. And this is why we're on this telecon to listen, because George has come up with a different way of thinking things. And I wanted the folks to see it.
Well, thank you, Pat. I can't think of a better statement to maybe close the official open part of this defense. Thank you, Pat, also for the RESCO, all the years that you've supported it. That's a tremendous initiative. And maybe it sounds, George, your next defense could be at NASA headquarters, maybe in the not too distant future of this work. So let's give George a hand again. So please, the faculty and committee members, lecturers, please stay here. Everybody else, I think, is invited in 218. Is that right, George? Or on the
Yes, please go to 33-218.